Okay. Hi, I'm Revill. I'm going to talk about my project to implement an LLVM backend for the Apollo guidance computer. So first of all, what is the Apollo guidance computer? Well, it's the computer used to put man on the moon. More specifically, Block 2, which was the actual release version of the Apollo guidance computer, holds the title of being the only computer used on the moon. So quick bit about the actual architecture. So the memory was von Neumann memory, but it was split into blocks and banks, which had to be dynamically switched between using an instruction. The memory and registers had no real distinction. It was basically just one huge block of, I think, about 4,096 locations. Data was represented with 15-bit words plus one parity bit, usually interpreted as one's complement, and sometimes interpreted as fixed point. Most instructions were accumulator-based, and they also had the concept of extracodes in order to extend the encoding space for the instructions. So why would I write backend for this? So firstly, to test LLVM's flexibility and find any weaknesses that could be fixed. Also to test my own knowledge of LLVM in the process, and also because it's cool. So firstly, how do I solve the problem of registers? Well, in the assembly, they're actually just aliases to memory locations, but I wanted to still define some special definitions so I could document them. And I did this for the first 8 registers. From then onwards, I just generated definitions for the entire memory space. And I also had to generate double memory locations, which were the combination of 2 adjacent registers or memory locations. I used register classes to generate something for the entire memory space to use in CodeGen, and also single register classes to use in instruction definitions. A quick bit about parity bits. So to accumulate the odd parity bit, I just accumulated what the current parity is with the next incoming bit and applied this in the MC code emitter. The decoder basically masks off this parity bit before decoding an instruction. Extend is the way that you get extracode instructions to be emitted. So if I'm emitting something in MC code emitter, I also need to check if it's an extracode and emit the raw bytes of an extend instruction beforehand. Parsing also needs to take into account extend. So basically I check if an instruction has to be prefixed by an extend, then I have to check if the prior instruction was an extend instruction. And I have failures if it's not an extend instruction or if a non-extracode instruction was prefixed by an extend. So in the decoder, I also have to implement a second decoder instruction table, which I check if the opcode is an extend. Then I check the next instruction and use this second decoder table. And lastly, a bit about some of the lowering. So multiply instructions produced a double word output, so it didn't match a standard multiply node. So I had to check for sign extends on the inputs and use a 32-bit multiply to match the double word output of the 16-bit multiply in the instruction. Similarly, divide instructions took a double word numerator, a single word denominator, and produced 2 outputs, which were a divisor and remainder. So for division and remainder, I implemented something that matches only this exact pattern and outputs the correct node. And that's everything. Ignore this slide because it's a lightning talk.